All right, so in this next module, we're going to talk about how we use those photoelectrons as the basis for a technique called XPS. So XPS stands for X-ray Photoelectron Spectroscopy. So clearly we're going to be talking about those photoelectrons that we just looked at. And we can characterize the composition because these photoelectrons are emitted from a certain shell of a certain atom, and we're going to be able to use that information along with the known information about our photons, our X-ray photons, the incident ones. So we can use that information um, and basically get a spectrum of values, and that's going to tell us what the composition is. And we know that it's going to come from a very narrow range of the surface of the material, and so we call it a surface techniques. And so this technique gives us composition of the surface region. All right, so our X-ray photon, the incident beam that's coming into our sample here, must have sufficient energy, and our equation for energy here is the h mu, in order to knock out one of those inner core electrons. For example, if this electron here is in the K shell of carbon, then these are the energy values in order to bring one of these electrons from that position to what we term the vacuum. So basically take it away from the atom. So we need 200 and at least 284.2 electron volts, the units here, in order to knock out that electron. So that's a fairly high amount of energy, but in actuality, we need much higher amounts of energy in order to do this. And so you can look at this table of these energies, and that's the energy that must be that's required to knock out these various atoms from the electrons. So now, if we think in reverse, if we hit a material with these X-ray photons, and we get a spectrum of different energies of how much energy it took to liberate those electrons, then that energy can be tied back to the element. So if in looking at the spectrum, I see that something took 284.2 eV to dislodge that electron, then I know it's tied to carbon K1s. And vice, all of these. So that gives us, and for example, if it was sodium, then I could potentially have multiple. I would have a K, an L, and multiple L's, and so forth. So how do we actually get that energy though? Because it's not straightforward. So we can use this equation here to obtain it. So the energy that we're after is so-called the binding energy. So the photoelectron's binding energy. Again, that is what is holding that electron in its local environment. So how much energy does it take to take that electron from an atom and move it away, so into the vacuum. So that's what this binding energy is, and we call this E for energy, and then the subscript is B for binding. So we can calculate this if we know the X-ray photon's energy. So this is where we need to, again, have the monochromatic wavelengths. So we know the wavelength and therefore the energy. So we know the X-ray's energy. And then we measure, the thing that we actually measure in XPS, this technique, is the kinetic energy. So we have a detector somewhere that's measuring the energy of that electron when it hits the detector. And so we term that E sub K for kinetic energy. And this is the kinetic energy of the photoelectron. The last piece of this that we have to sort of almost correct for accounts for the energy that's required to escape the surface. And so this is known as the work function, and it's going to depend on the specimen and also the spectrometer. So this is, if you remember some of the correction terms in EDS and XRF to do with the matrix factor. You know, this is kind of akin to this. This is how much energy it requires to escape that, and it really does depend on the specimen and the spectrometer. So there has to be some corrections done here. Excuse me. What we end up plotting in these for XPS is binding energy. That's what we're after, because we can look up the binding energies for the electrons in various elements and the various states in that element, and those are characteristic of that element and of that position. So just like we can use X-rays, the characteristic X-rays to identify an EDS, we can use characteristic or these photoelectrons with characteristic energies in XPS. And so that's what we're doing. So here, if we look at this, here, this peak right here. So this is about 285 electron volts, and this is binding energy. And one thing you're going to notice, we'll talk about this more, that binding energy increases to the left, which is something new. And then we have counts. So we're looking at a spectrum. So that we can tie to the carbon 1s peak. Excuse me. And vice versa. And you know, with a lot of these others, we can do the same. So the one down here is tied to fluorine 1s because it has something close to 7,000. And we can, you know, identify all these peaks based on their characteristic energies of those photoelectrons. So in XPS, the first thing we end up doing is we obtain what's called a survey scan. And so that's a scan of a very wide range. So we go from 0 all the way up to 1,000, a very wide range of binding energies. And this is to be able to see all the different things that we have. So you see the labels here. So we have aluminum, carbon, oxygen, and you can see the 2p, 2s, 1s, 1s. Those are the specific shells that they're coming from, or subshells. So that's one part of it. But one thing that kind of complicates matters in XPS is that we can also have Auger electrons. So there's nothing precluding, even though we call it X-ray photoelectron spectroscopy, there's nothing precluding Auger electrons from occurring. And so when you see the oxygen KLL, or 3 letters there, that's tied to an Auger electron for oxygen, or in this case carbon. So that can kind of complicate matters for XPS. We also, along with the survey scan, we also tend to focus on one element in the binding energy. So instead of scanning a very wide range, we only scan a much smaller range, 10 to 20 eV. And this is to just look at one element. So for example, this is the area where we're going to see sulfur 2p. And what we see is that there's actually 2 peaks. But again, 2 peaks doesn't mean that it's a different element. We can have multiple peaks because there are different multiple energy states in the 2p. And so the other distinctions that you often see is that you'll see fractions. So we have, in this case, the 1/2 and the 3/2 peaks, and these are tied to the total momentum. So we kind of separate out the different peaks for a subshell based on the total momentum. So you often see fractions there. So a P will have 2 peaks, 1/2 and 3/2, and F will have 5/2 and a 7/2. So this is tungsten. The 4F for tungsten has 2 peaks here. And again, those fractions are tied to the total momentum J that we talked about in a previous section. All right. So based on this, and if you want to look at your textbook here for those various values that we have, I showed you snippets from the table there, but if you go to the section on XPS in your textbook, using that information, looking at the survey scan, see if you can identify these elements that are in this scan. So we've labeled the transitions, but not the elements. So see if you can, using the values here, see if you can determine what these various peaks correspond to. And this is just one element. So we only have one element. We're not looking at multiple elements here. So this is a scan for a pure sample. What sample is this? Pause the video, see if you can determine this. We'll come back and discuss. All right, so then now that you've had a chance to examine the table in the book and see if you can identify the element shown here in this XPS spectra. So again, binding energy goes up. Let's take a look at what we've got. So this is table 7 one. It's the XPS positions of the elements irradiated with aluminum X-rays. So these are all in EVs, electron volts. And if we look at the various, they're going to have multiple positions for various elements. And so, if you find kind of one value and then trace it back. So if we maybe start with this biggest peak here, which is the 3D, labeled as a 3D, it goes from 0 to 1,000. It's not written entirely well, but let's say 1, 2, 3, and then maybe about 370 or so, 375. And so if we look at D values for that, we see that, yeah, this is around 3. The closest one appears to be this 373. But then if we start looking at other ones, so let's look at the 3P here. This is 1, 2, 3, 4, 5, and then 570 or so. And we see the same thing. We have a 570. And if we go through all of those various peaks, we'll see that it matches up with this one, which is silver. So that tells us this is the survey scan for silver, pure silver, that we have, right? So we're just comparing those values in this spectra to values from known elements. So just like you would with any kind of spectra. But again, remember, these are the binding energies for the various electrons in silver. So basically, these are all the electrons that are getting knocked out from the inner core electrons of silver. And we also have some Auger electrons. Anytime you see that M and N, those 3 letters, that's the designation for Auger electrons.